Hi, in this video we're going to analyze this amplifier circuit. This is a common source, self-biased with a source resistor on the source side. All right, we're going to work out the four components here: the input impedance Zi, seen from the input side, the output impedance Zo, seen from the output side, the overall gain, voltage gain (AV), and the overall current gain. All right, um, let's begin. So as usual, whenever we want to do an AC analysis, we need to convert the original DC circuit into an AC equivalent circuit. We're going to put it over here, all right? And these are the three steps that you have to follow. First, you have to short all capacitors. So in this case, it's only C1 and C2. That will become a short, a wire, right? You have to zero all DC sources. In this case, it's only one, VDD. So that will become 0 volts, which means it's connected to ground. And then finally, we replace the device, which is this JFET here, with an AC equivalent model, which is over here. A very simple model. It has only one dependent current source, GM VGS, where VGS is the gate to source voltage. All right. So let's have a look at the right-hand side of the device of JFET. So we have VDD that's going to become 0 volts, which means it's going to be grounded. That means the top part of RD is going to end up ground. The other part connected to drain. And VO is also directly connected to drain once C2 becomes a short. All right. And then on the source side, RS will simply connect from source down to ground. So let's have a look. All right. So you have RD between drain and ground. This is the ground part. And you have RS between source and ground. Everything else remains. So VO is where it should be. ZO is where it should be. IO is flowing towards the drain. Yeah, towards the drain. So IO here is also flowing towards the drain. Remember, yeah, RD is flipped upside down. So that's why IO now points up instead of pointing down. Okay. And then on the left-hand side, fairly straightforward. RG is between gate and ground. And VI connects directly to gate. All right. So VI, that's VI, connect directly to gate. II flows from the source down RG. Remember, yeah, this is open circuit, so that means no current will flow into the gate. That is a feature of field effect transistors. So II will go across, come down, and go back to the source. All right. Okay, so let's work out expressions for IO, II, VO, and VI. That will be useful for us to work out the four components of interest. So let's start with IO. All right. Well, IO is a current that flows up that way and then goes left because there's nothing here. So it goes up, goes left, and comes down. Well, it is actually GM-VGS. So IO is actually GM-VGS. Comes down, goes across, and goes back up again. So straightforward, IO is just GM-VGS, right? So by KCL, so IO is just simply, IO is simply GM VGS. Okay. All right. So next, let's have a look at II. II is, you can look at it in terms of Ohm's law. You know, I equals V over R. V is VI, and R is RG. All right. So this is in terms of Ohm's law. That II is simply I equals V over R. V is VI over RG. Okay. Okay, so we'll leave VI for now because we're going to work out what VI is a little bit later. Oh, how about now? Let's do it now. If you look at VI, VI is from this node, the gate node, to ground, which means I can describe it in terms of these two voltages. The voltage across the gate source, which is called VGS, and the voltage across RS. So I can write VI in terms of this plus that. All right. So this is more like this is a KVL. So I can write VI is equal to VGS plus the voltage across RS. Well, I'm going to call it VRS for now. All right. So, well, what is VRS? Well, VRS is the voltage pointing upward. So it's actually the current GM-VGS through RS, right? So GM-VGS is coming through RS. So again, just simple Ohm's law. So our expression now becomes VRS becomes V equals IR. I is GM-VGS. And R is just RS. Oops. Capital S here for source. All right. Oops, sorry, this is a plus. All right, so we can factor out VGS. So VGS multiplied by 1 plus GMRS, right? Okay, so that is VI. So let's plug this in straight into the equation that we have earlier. That's the one up here, right? So that's just equal to, that's the top part divided by RG, all right? Okay, you can't simplify anymore. So that's II. Let's have a look at VO, right? VO. Well, VO, again, very simple Ohm's law. So V equals IR. I would be the IO that is in the opposite direction because we want VO to be positive, right? Pointing up. So that means IO needs to flow down, all right? But since IO is flowing up, we'll just put a negative sign in front of IO to indicate that we have a change in direction. So this is just simply Ohm's law. So I just add it up here. So VO is going to be equal to because IR. I is negative IO, right? Remember, yeah, it's flowing in the other direction times RD. Okay. Since we know that IO is GM-VGS, so therefore this expression becomes negative GM-VGS times RD. All right. So that's our expression for VO. Okay. So we have, we have the four of them. So we have IO, we have II, we have VO, and we have VI. So let's work out the expression for ZI, ZO, AV, and AI. So let's work out the first one, which is ZI. This should be straightforward because the input impedance ZI, the only thing you're going to see is RG. There's nothing else. This is a break, right? So therefore, there's no current flowing in. So therefore, RG is the only thing that will be seen by the input voltage VI. All right. All right. So let's do ZO. Okay, so ZO is the output impedance seen by VO, right? Now, you always have to remember whenever we're working out the output impedance, we have to zero the source, which in this case is VI, right? So we need to zero the source. That's VI. So when VI is 0, well, we can look at this KVL equation here. VI is equal to VGS times 1 plus GMRS. So the only way that VI can be 0 is if VGS is 0, because the rest cannot be 0. So VGS is the only possibility, is the only component that will be 0. So when VI equals 0, VGS is 0. Now when VGS is 0, GM-VGS is 0, which means it is now 0 amps, which means this is now an open circuit. So then the only thing that ZO will see is actually just RD. So straightforward. So ZO is just simply RD. Okay. Let's move on to the next one, the voltage gain. Now the voltage gain is defined as the output voltage divided by the input voltage. And we have expressions for both. So VO is just simply negative GM negative GM VGS RD, all divided by VI, which is VGS bracket 1 plus GM RS. All right. Okay, so obviously VGS cancels out, top and bottom. Okay, so what's left is just negative RD, negative GMRD divided by 1 plus GMRS. Okay, that's our expression for the voltage gain. Finally, let's work out the current gain, which is defined as output current divided by input current. All right, and IO, we already have an answer, is GMVGS. So that's just GMVGS divided by II, which we also have an expression, this slightly long expression there. All right. So again, VGS cancels out, top and bottom. All right, so those guys cancels out, and then RG flips to the top. So what you have is GMRG divided by 1 plus GMRS. And that's it. Hopefully you agree it's relatively straightforward. See you in the next video. Thanks.